overview today about the university in Siegen and then my institute for engineering and thermodynamics, and I will show some parts of research what we are doing, not to take too much of your time. So, let's see. Okay. So here we just have the map from Europe, and here we have Germany, and here is Siegen in this area, so you can go there by plane to Frankfurt or walk somewhere there and move by train to Siegen to find us. And here you could see it's a picture of the city. It's a small town, a little bit more than 100,000 inhabitants, so really not comparable with the size here. Nevertheless, it's a city surrounded by a lot of hills. Here you can see the inner city, and here in the back on this hill is part of the university. It's spread all over the city in different buildings, but engineering is located over here on top of this hill, so you have a nice view around the countryside. The university was founded, it's a young university, it was founded in 1972 and was renamed to the regular university in 2003. And as we can later see, it offers education in quite a number of different fields. We have everything divided into 4 faculties, each with a lot of different departments. Number of students is right now around 20,000. And we have approximately 1,200 foreign students from, well, everywhere around the world. Right now, majority maybe from China. And the university has 1,500 employees and 600 of the academic staff is full-time there. So here you can see these 4 faculties. Faculty of Art is one, Faculty of Education, Architecture and Fine Art, Business Studies, Economics, Management Information, Economic Laws. And we are situated here in Faculty 4, Natural and Engineering Science, so we look a little bit closer into this right now. Concerning education, you can have bachelor and master courses. Here are some master courses which are taught in English. It's chemistry, physics, mechatronics, and PhD degrees you can of course obtain in all faculties shown here. When you have started bachelor study, it normally takes around 6 semesters, and it will finish with a bachelor thesis, which is approximately 1 semester already within these 6 semesters. Master is following. It has a duration of 4 semesters. And the last semester is also, the 4th semester is also for your thesis, where you have a certain scientific topic which you should investigate during that time. But I learned it's quite similar here. And let's have a look into the faculty 4 with the different departments. Here we have biology, chemistry, civil engineering, electric and electronic departments, engineering, computer science, mathematics, mechanical engineering, physics. And I'm situated over here in mechanical engineering. So, of course, let's have a look closer there. Well, there you can have, in faculty 4, you can have a lot of different master degrees. As you can see here, you can start with A and then end around here with T, so with automation, going over chemistry, civil engineering, computer engineering, industrial engineering, mechanical engineering, and so on. So these are the different master degrees you can achieve in faculty 4. And our department of mechanical engineering, where I'm situated, has different institutes, as you can see here, Institute of Mechanics and Control Engineering, Institute for Design, for Production Engineering, Mechanical Energy Engineering, Vehicle Technologies, Material Engineering, and I'm situated in the Institute for Fluid and Thermodynamics, and here you can see the different chairs here, and This is my institute, Engineering Thermodynamics. So within this department of engineering, there are at least several bachelor and master options you have. Mechanical engineering, bachelor and master. Also, a binational language degree you can get. So courses are taught also in English. International project engineering management, industrial engineering management, material science, automotive. As you can see, everything has 6 semester bachelor, 4 semester master, as I already said at the beginning. So let's have a closer look what we are doing in science in our Institute for Engineering Thermodynamics. We have we started around 3.5 years ago when I reached Siegen. I was before in Erlangen, and well, my basic subject is to use optical diagnostic techniques, laser-based techniques for sensing gas, sensing combustion diagnostics, and so on. So we divided our group into one section for development application for laser diagnostics, for gas phase sensing, for example. Then what we develop over here, we use over here, for example, for spray diagnostics or combustion diagnostics. What we develop over here, we use, for example, at our engine test facilities in order to investigate what is going on in the combustion process inside an engine. And beside this, what has been done before in this institute is conventional analytic techniques, like, for example, absorption analysis, and this we are still doing, and sometimes we combine this also with our laser diagnostic techniques. So this is more or less what we are doing, and I will give an overview over the laser diagnostics we are doing, and then we will see our time is running on if I could show some other areas. But up to now I thought about talking about half an hour in total, and that's some examples out of these. So we go into this. All in all, we have 10 people working here in my institute that are scientists, and they are. And in addition, we have something like 5 to 6 bachelor and master students working there and helping us with our experiments. So let's start with laser diagnostics. We are using a lot of different laser-based techniques. For half an hour, or even less now, I just focus on some which are highlighted over here. That means Raman scattering, laser absorption, laser-induced gratings, and coherent anti-stop Raman scattering. As you can see, all are applied to get some information from gas phase, like gas phase concentration or temperature, or even both. So for all these things, I will show some examples. I will start with the linear Raman scattering. That is a very nice and easy to apply technique. By this technique, you illuminate a gas probe with an intensive light source. It need not to be a laser. When this effect was first seen experimentally by Sir Raman in India several years ago, he was born and lived and studied quite a while near Madras, where I was 2 years ago. It was interesting to see. He had no laser at that time. It was during turn of centuries. So his intense light source for generating this Raman effect was the sunlight, which he used also filters to filter out certain wavelengths of the sunlight. Now we are happy that we have lasers, so we can use this device, which makes life a lot easier for us. So we have laser systems. This laser system is focused into a gas volume. There it interacts with the molecules, and as the name says, linear Raman scattering, there's a linear interaction between the incoming intensity, the Raman, the intensity which is send out the answer which is sent out by the molecules and the concentration for a certain temperature. So when you have a constant temperature and you look at your answer, your stray light, your reflected light from the molecules, you have twice as much signal when you have twice as much molecules, half the signal when you have half molecules. So it's a linear dependence between concentration and signal intensity. That is very interesting for us engineers because it's an easy way of making calibration and then building up a device based on such a calibration. So using such a laser source, focusing into measurement volume, collecting the signal, and the signal itself what you do is here you look which energy levels of the molecule are occupied. And you get then an answer from the molecule concerning its energy levels. So you have a certain fingerprint for each different molecule. And here you could see different molecules. Here, for example, nitrogen. Here, methane. Here, higher hydrocarbon. Green, CO2. So you get a certain fingerprint from each molecule. And in order to get to measure at which wavelengths you get your signal, you have a spectrometer and the camera down here. Of course, you have to separate between these nets of different molecules, but it is possible. And it's a very simple device. You have a laser inside this box, you have a cell inside, gas inlet, gas out, switch for on and off, and your computer for controlling all things. So here you could see two different gas probes from two different places. One here from Russia, one from the Netherlands. And you could see the differences in the signals already by eye. It's very easy to see. You could see, over here we said it's nitrogen. Here you can see only a small amount. Here you can see a much larger amount of nitrogen here. So it's around 10%. Here it's around just 1% nitrogen. Then you have this large peak here from methane. Also here you could see some amount of CO2, and you could see it also in, let's see, over here, 1.2%, here nearly 0%. And here you have higher hydrocarbons, here you have less hydrocarbons. You can see it in this list. So based on this, you can investigate natural gas and see the difference. This is of course of interest when you buy some amount of natural gas in order to use it for heating purpose or whatever, or to use it in a gas turbine to generate electricity. You want to buy something which you can burn. You don't want to buy nitrogen. So when you buy gas with a huge amount of nitrogen, well, it should be cheaper than one which has a high calorific value, a high energy value. So it is interesting out of these concentrations to calculate the calorific value, that means to calculate the energy contents of this gas. And that is of course a basis for your payment for this gas. And, it's also an information which you need when you want to control a combustion process, because you want to optimize it and you don't want to waste energy. So this is of course important, and we made measurements with our device at different places. Here is, for example, we made measurements in a gas turbine doing production of electricity in Karlsruhe at a gas turbine. The gas turbine is situated down here. We measured several days, and we measured in the supply pipeline for this gas turbine. And here you can see the student starting the device. The gas turbine is beneath here. There was just a thin metal wall here to the outside. So when the sun was coming around, we had sunlight. It was quite hot on the day, cold during night. We had temperature changes, vibrations from the gas turbine. There was some dust. Nevertheless, we measured over several days, and you can see here over some time the changes in gas concentration of the different species And here, this is the Bobbe index, and it's a measure of the calorific value. It's density weighted. But nevertheless, you could see even here in methane, you could see concentration differences. And when you think about adiabatic flame temperature, and you look at these differences, there's approximately 100 or more degrees in flame temperature, which will change due to these changes. So it's interesting to have this information about the gas concentration, maybe to further also control these processes. But of course, we have some more examples of this, not only gas turbine. We measured also in an engine at the MAN diesel and turbo in Copenhagen. It was a ship engine. It's a 4-cylinder 2-stroke diesel engine. It has each cylinder has a diameter of 50 centimeter and at a height of 2.2 meters. So you can more or less walk in there and clean it from inside. It's that large, and it's just 120 RPM. So it's very slowly driving diesel engine, which is used for ships. You can see it, and when I was standing here beside on this platform, and maybe my hand could reach this point or something like this. So it's quite large, and the idea is in the future to, or even already ships are sold with this technology, to use not only diesel fuel or heavy diesel fuel, which is highly polluted, but to use LNG and CNG, that means compressed natural gas, for example, or liquid natural gas, in order to run these ships, especially when they are near the coast, in order to fulfill future regulation. There is one coming next year, that is TI3, and which could not be fulfilled with this crude oil, so they need to have some new technology. And the idea is to have engines which run on both, so when they come into the region where they have to fulfill this emission regulation, they switch on to LNG or CNG, to gas. They use gas in the harbor also, and when they're far off and no one takes care, they switch off the gas and use their highly polluted oil again. But of course, this already helps in harbor regions to reduce pollution. And this was a test facility where we made measurements in the gas supply line for such an engine. And they need an amount of a few tons of gas per hour, which is going through the pipes, so quite an amount. And in order for safety regulations, before they start, they purge all the pipelines with nitrogen. So all the pipelines are purged with nitrogen, filled with nitrogen, and then they start the gas supply, and then they also start the engine, and then they make the test. But of course they need to get rid of the nitrogen with these lines, and this nitrogen is going through the engine, and after a while the lines are free of nitrogen, the engine is running with the gas, and then you have the normal operation. But you don't know how long it will take to get rid of all this nitrogen. And here you can see we measured in the supply line. You have here, for example, the nitrogen line was full of nitrogen. After some while, it's disappearing, and it took over to 50 to 20 minutes to get down with the nitrogen. You see that higher hydrocarbons, including methane, is coming, so you have natural gas in your line. And you could see again the differences. Of course, clearly we learned here in the back is nitrogen, high amount over here, and when we are here in the normal operation mode, it's quite low. And by this, they know, okay, it will take around 20 minutes to have a normal engine operation. Then we could start with our measurements, exhaust gas measurements, and so on. Then you can run the engine in normal mode. Otherwise, they don't know. And there are some turbulences within the pipes, there are some bendings and so on, and there the nitrogen is stored for some while, so it's completely off the line. Another aspect is completely different to this, and that is medicine. That's something we have done just a few months ago in a clinic in Erlangen. They have a test center for anesthesia procedures. And there we used also our Raman device and looked in comparison to a standard anesthesia monitor what are the advantages. These standard monitors could not measure nitrogen or water vapor, and they measure, of course, all the rest. But these are, of course, molecules because nearly all molecules are Raman active, except argon, krypton, neon, and so on. So these noble gases, but they are very rarely used in processes. So all of these we can address also with our Raman system. And we want to know how good we are in comparison to such a system. So this is not a real patient, it's a dummy, it's a simulator, but it's also a breathing system. So behind this is a room full of gas bottles and electronics. So this is breathing like a patient which is under surgery, and medicine students can test their knowledge there and can train before they move over to patients, and we could train our instrument and see how it works there. And that we have done in comparison. These are really very new results. We'll present in a few weeks in the US on a conference. Here you could see the comparison. These dots are the measurements from the standard monitor from Traeger, and these measurements here, these curves, are what we have measured with our Raman device. So we can measure, of course, nearly exactly these values, and beside this we can get information, additional information from nitrogen and also from water vapor. We didn't monitor it, we didn't plot it here in order to have this comparison to the Jaeger instrument. But we, of course, we measured it, and if we look into some minutes more detail over here we have a minute time scale, we have seconds. You can see the breathing cycle, that's the up and downs over here, and you can see it also over here. And what happened is that in order to see some differences, the simulator changed the concentration, for example, the one for oxygen and for water vapor also, and increase the oxygen, reduce nitrogen, and you can see this criteria. So this works also over there. Nevertheless, we had here time resolution around 1 second, and that's a little bit too slow for such a device. But we already modified it to get down to 100 milliseconds, sorry, and that is probably possible for the next test run, which will be 1 or 2 minutes. So we switch over to another technique, laser absorption spectroscopy, which we have done also in a way that we, well, here you could see the basic principle first of all. You have a diode laser, you have a lot of institutes working also with laser absorption spectroscopy, so that's in principle not useful to you, for sure. You have a diode laser, you have a gas volume, and you have a detector and photodiode, and the absorbance is measured due to Lambert-Bell's law, and it's depending on the concentration within your gas sample. And by this you have the possibility to get a concentration information. In order to get this, you normally change the wavelength of the diode laser to sweep some certain wavelength region, which is typical for one molecule to get 1 or 2 spectral lines from this molecule. So you get a concentration from one molecule. This is nice, but very often you want to have more than one species at a time. Then you need to expand your scanning range. It's not very easy concerning cheap diode lasers, because they make mode hops and they have a certain range which you can change by temperature control. by temperature changing. The other idea is not to use a laser diode. Here we have an idea using a nanosecond laser, high-red laser in the infrared, run this through a photonic crystal fiber, and this photonic crystal fiber makes out of one certain wavelength, a wavelength region of several hundreds or even thousand wave numbers. So then you have a huge spectrum coming at one time. After this photonic crystal fiber, you run this spectrum through a dispersive single mode fiber of quite a length, 25 kilometers. Okay, you need not to put it around your building, it's just to roll like this. So it's not a large device. But by this, you get different colors out of this fiber at different times. So you get red at one time and blue at a later time. And you put in a filter because you have, due to the dispersion, there's 2 times, so you just get one arm out of this, and then you have exactly at a certain time red and at a certain time blue. Then you know first is coming red, and then it's coming blue, or vice versa. And then you measure this in your photodetector and as a reference and put it into a gas cell. And then you have a scanning of a large wavelength region in your gas cell. Not only a few nanometers or few wave numbers in order to scan one molecule. Now you can scan much more molecules at once. And it's a very fast technique. You get within milli or even microseconds you get your result on the photodetector, on the oscilloscope, and you can see here what you could measure in time and concerning intensity. At the end you have a signal which over time which gives you the different species, and one example for you here for CO2 and methane, and you could see the absorption lines for CO2 and for methane going over quite a wavelength range of several hundreds of wave numbers, which would not be possible with just one diode laser. Of course you could say, okay, I just use 2 diode lasers, it's even cheaper. Yeah, you're right. But keep in mind that you maybe do not want to measure just 2, but 3, 4, or 5 different species. And for each you need one diode laser and a photodiode. So at a certain point, this system is simpler than the one with the diodes. So this is something we have done. Just one example. Another example is a little bit more complicated. And I even choose the most complicated situation for this. This is called coherent anti-Stokes Raman scattering. Okay, one well-known word in there, Raman scattering. We learned already about that. That's good. Second thing is that it's some more words. It's a coherent process, and it's using the anti-Stokes part of the Raman signal. That's also okay, but it's a non-linear process. That's bad, because now we have no linear combination between signal intensity and concentration. We have a non-linear combination. You can see over here the intensity of your signal is non-linear depending on the concentration, which is hidden between this susceptibility over here. So by this, it means this is a process which is not, where you could not easily use calibration. When you use this process, you need also to calculate energy levels of molecules in order to calculate what signal you might have. And because of this non-linear process, you also need not only one laser to generate your signals. You can see over here, this is the signal, it's an energy diagram. You need more than one, at least 3 lasers. So you have a 4-wave mixing process or 4-photon process. It's like using billiard balls on the table. You have 3 incoming balls colliding with the fourth one, and the fourth is just moving somewhere away, and the fourth is your signal. So, and in the same way, you have here also energy conservation between your incoming photons and your generating photons. That's the billiard balls on the table. And also momentum conservation, also like your billiard balls. So there is some comparison, at least the photons are small. Concerning the temperature here, you need to know, or you need to calculate energy levels and how these energy levels are occupied by a certain temperature. Number of molecules in a certain energy level at a certain temperature. So that's Boltzmann distribution. You have to calculate this, and you have to calculate your signal and calculate it, for example, for 20 different temperatures, starting at room temperature up to 2000 Kelvin or degrees, and then compare this calculation with your measurement. And the best fit is a temperature. It's temperature measurements. You compare zero law of thermodynamics. That's also what we do over here. Okay, you can do this, but you still have some problems. It is used by our institute more or less very often in this way. But still there are some problems with this technique. We're using nanosecond lasers very often. The problem is that we have, besides this resonant signal, also unwanted signals. Non-resonant signals from all other gas molecules, sometimes resonant signals from some other gas molecules which we don't want because we can't calculate. Think about complex molecules like water, C2H4 or whatever, calculate the energy levels. It's not that easy. We tried already, but it's not that easy. So one idea we had, and we tested that together with Sandia Labs in Livermore in the US, was not to use nanosecond lasers, but to use picosecond lasers. Here you have a picosecond laser and 2 more picosecond lasers over here, and then you have the signal. Good question, what is the difference? At least when you don't have any time delay or time difference, no difference. But when you think you excite your energy levels and the readout laser is delayed in time, you read out your signal later, then all your non-resonant information will already be decayed, because that is in energy is in levels which did not last very long. But the resonant processes last much longer. So when you read out after some time, you just read out the resonant processes. And these you can calculate. So then you just read out the signal which you want. The rest you just forget. And that we have done, and we are also doing that now in Siegen. Here with a nearly black laser, which could be varied in pulse width between 50 and 250 picoseconds. Here we use most of the time something like around 110, 120 picoseconds. And in Siegen we are now using one which has 100 picoseconds. And pumping dye laser and using a dye laser together with this nearly black laser, focusing these lasers. Here our 3 billiard balls are coming, hitting the 4th ball, generating here at this measurement point the signal, and then the signal is going with a detector to a spectrometer and a camera. We look at energy levels, all the things you have seen from the Raman series. Okay. And when we look into time, how the signal is decaying over time, you can see here in black lines the non-resonant signal. For example, from argon. This is just one example for a non-resonant signal, because argon has no resonances. So this is decaying extremely fast. After something like 200, 250 picosecond, it's decayed by, well, 4 orders of magnitude. Our resonant signal for nitrogen, for example, is just decaying 1 to 2 orders of magnitude. So that's much better to get your resonant signal at a certain time delay. And the situation at higher temperatures is even better. So then you have just your desired resonant signal, and you can suppress your non-resonant, unwanted 4-way mixing processes. This is just one, there are much more. And this could be applied, for example, to study flames. We use this in a shooting flame, for example, and compare our temperature measurements with old thermocouple measurements. And another aspect is, we published this somewhere a few years ago, and another aspect is when you look into the decay curves, the rate of decay is a measure for the line width. By this you could measure also molecular line width. That's extremely simple, just monitoring the signal, delaying your readout laser, and just taking this signal every few picoseconds. And just making such a decay curve by integration over the area below the signal. Then you have directly information about line width, which you normally could not measure that simple. But this information about line width is needed when you want to calculate such energy line. So by this we get also some line width information, which we showed last year. And one further thing is, with picosecond laser system, is for this cast process, not energy of the laser is important, but intensity. Energy is important for linear running processes, but for the efficiency here, you need intensities, laser intensity. So when you have short laser pulses, you increase your intensity. And when we have picosecond lasers, which have something like 100 millijoules, we normally use, and you have 10 to 100 picosecond time, this is much more effective than having 1 joule green laser in 10 nanoseconds. And up to now, it was very difficult to spread these lasers up to a laser sheet and to focus 3 sheets in order to form a line in the crossing section and to measure along a line temperature. Up to now, it was just point-wise. We've done it with a joule green laser some years ago. We showed that it's in principle possible. But with a nanosecond laser, it's much more difficult. With these picosecond systems, it's extremely easy. And here you could see measurements through a flame. It is here you could see different areas of the flame. This is outside, and you get some lines from nitrogen and air, and it's cold. At higher temperatures here within the flame front, this higher energy levels are occupied. You can see higher energy levels appearing over here. Just nitrogen is there, and if you compare it with the calculation, you can see the best fit is 1930 Kelvin, and if you go again to the outside, it's getting colder. So this is also possible. We have done much more also in the other subjects here, but I think I had already spent quite an amount of your time. So by this I would like to finish today. I would like to thank some people, hopefully you can find them. Let's see, yeah. Exactly. First of all, I've given you an overview of the university, showed you what is possible concerning different studies, bachelor and master studies, PhD degrees, which different areas we are addressing. And I've given you some information that what can be done with optics and laser diagnostic and thermodynamics. Just a short, small overview of what we are doing. As you have seen, there are some more areas, but maybe next visit is coming and tell a bit more about this. On the next visits, showing some research activities from very simple devices which are nearly finished, like this Raman device, up to very quite complicated things like these coherent anti-stop Raman technique with a lot of lasers and picosecond systems, time delay, and so on. But you can get physical properties out of this. You get thermodynamic information out of this, temperatures, concentration. That's definitely possible. And of course, I would like to thank a lot of people who have worked on these subjects with me together over time. And of course, a lot of people, the same for funding. You see some. And I would like to thank you for your attention. And looking forward to your question. So, based on this, there are no silly questions. The only thing is I didn't explain it good enough. So please ask whatever you like.
What about wave light excitation laser in first work?
For Raman, okay, yeah. That's a good question, because that is one advantage of this linear Raman. Because in principle, for the Raman effect, it doesn't depend which wavelengths you use. So you have to think about, because you're collecting photons, where do I get the most photons? The Raman cross-section is depending on fourth power of your wavelengths, or inverse wavelengths. That means blue is better than red or infrared. On the other hand, you have your detector. So when you go into infrared, you have your Raman shift. You go into a wavelength region which you could not address by typical silicon-based cameras. So you better go down to green or blue region. Then you have your detector still working nearly in the visible range. But then you have to think about your laser source. Do I get a cheap, good laser source in this wavelength region? And are there any other physical processes, like laser-induced fluorescence or whatever, which might influence my signal in this wavelength region? That's something you have to have in mind. So, but because you're free to choose your wavelengths, you have to make up your mind concerning these questions in advance, and then decide which wavelength. So there's no one wavelength every time. It's one wavelength for your question or for your application.
Понятен ответ? Нет. Пожалуйста.
Also, one question to this very setup what you asked about. Just so you told that you had first some opportunities to go with a time delay of 1 second or time resolution of 1 second, and you could lower it now to 100 milliseconds?
Yeah, something like this.
I would just like to have some knowledge about how, so just do you brute force your way into it with like harder lasers or better diodes, or is there some other opportunity you can change your setup?
The options you have is better laser, better detector. There are two options. The other thing is the Raman process is not a coherent process. So the signal is spread all over the complete room. It's not a certain direction. That means when you get closer to the source of generation, you can collect much more signal with the same diameter of lens. You can get closer, you can use larger lenses to collect more signal. That is an option. You can use higher laser power, you can use better detectors, and that is an option to increase the signal. So it's no magic behind it. It's really what you say, in order to get more photons, more energy in laser, more sensitivity in detector, or larger lenses to focus this, to reduce losses of signal. That's exactly what you need to do to increase.
Пожалуйста, еще вопрос. Да, конечно.
Правильно ли я понял, что основные интересы вашего института научного сосредоточены в области газоанализа?
Aber ich habe nicht verstanden. Ihre wissenschaftlichen Interesse sind Gasanalyse.
Yes, we are interested in gas analysis in different areas. We started a long time ago from combustion.
В различных областях сжигания.
Именно газоанализ или разработка новых методов и средств его расшифровки и так далее.
Gasanalyse oder neue Methoden und Instrumente für die, для чего?
методы и средства измерения там,
Oder Methoden und Mittel für die Messung. Also was ist ein Ziel?
Okay.
Gasanalyse oder neue Methoden?
Okay.
Я уточнил еще, какова цель? Газанализ или новые методы? Правильно спросил?
What we are doing is, here we develop devices, measurement techniques, and develop it for gas analysis. Look if they are working. We apply them in these areas for spray diagnostic, for combustion diagnostic. We apply them in our engine test facilities, or we apply them in combination with conventional. So what I've shown is just this part where we develop these things. You're right, you have seen just development. But we use it also to get information. But this is done in the other groups. So you have seen just one part of the main system.
Also die beiden sind fest verbunden.
All parts are connected. All parts are connected. These things were used in the different areas. But in this today, this time, I've shown only this one. The rest I can show next time, or even now for interest, but it takes again some minutes.
В заключение можно еще вопрос? Извините, а вот основными заказчиками ваших научных разработок являются в основном предприятия автомобилестроительной промышленности. Вот судя по последнему
У вас все, где сжигание идет.
Но что преимущественно? Что это автомобилестроение?
Welche Gebiete machen Sie das? Ist das also Schwerpunkt Automobilindustrie oder что-то второе? Oder was anderes?
Okay. We work for automobile companies, Volkswagen, Mercedes, and so on. But we work also for gas turbine firms, ENBV, for example, ship engines, MAN. Yeah, but also for other companies who are dealing with gas transportation, biogas companies. So everyone who wants to know something about his gas quality. In the conventional part, we also investigate filters which were used in passenger cars to avoid that fuel is coming out of the tank. When you go into a parking lot under earth with your car, and you keep it there for several days, and you come back, you will not smell any fuel, and that's because of these filter systems. Nowadays, they changed the fuel in Germany and in parts of Europe and put in some ethanol in order to reduce the oil consumption or the gasoline consumption. And this has effects on the filters. So we investigate also these filters, for example.
Ну, я все переводить не стану. Значит, он говорил о том, что для них также большая проблема это вот фильтрация, обычная фильтрация. Я тебе рассказывал про автомобильный выхлоп, в частности. И они используют это, в частности, как первичную информацию. До сих пор. Я тоже хотел бы поставить один вопрос в продолжение того, что вы спрашивали. Меня интересуют несколько более приземленные вещи. Вы уж меня извините, я по-немецки спрошу, мне это легче, потому что по-английски мне надо сначала у меня фразу составить. А по-немецки я потом переведу, что я спросил. Also, Entschuldigung, meine Frage stelle ich in Deutsch, weil für mich ist das viel besser. Ich muss zuerst in Kopf übersetzen, dann sagen. Also, im Grund. Sie messen praktisch mit unterschiedlichen Laser für Spektroskopie. In Messtechnik, in Gasen, es gibt nach meiner Meinung zwei Grundprobleme. Erstens, kontaktmäßig. Sie haben einen Sensor. Er hat Masse, er hat zum Beispiel Wärmekapazität und so weiter. Und deswegen er integriert in der Zeit. Hier, Ihre Methode. Sie schicken einen Laserstrahl und es gibt ganz bestimmte Messstrecke. Sogar wenn danach geht das so, wie Sie erzählt haben. Es gibt ganz bestimmte Messstrecke. Und Sie haben Integral in dieser Messstrecke und wahrscheinlich zerstreuen Kalk, ein Konus. Das ist auch ein Problem. Was können Sie davon sagen? Entschuldigung, ich übersetze für Sie. Я спросил очень простую вещь. Вот при такого рода измерениях есть две проблемы. Когда у нас измерение контактное, ну вот, допустим, температуру измеряем, вот этот штырь надо нагреть. Значит, вот это, он работает как фильтр, и какие-то быстрые изменения он просто сгладит. То есть он дает интеграл по объему. Вторая проблема, это когда вот здесь вот есть какой-то путь, на котором происходит измерение. И по пути, даже если потом луч рассеян, как вот он объяснял, и по пути у вас получается в конце концов какой-то интеграл по объему. И все равно информация получается недостоверной. Вот я попросил просто пояснить вот эту проблему. Да. Yeah,
okay. So, thank you for this very interesting question, or at least two questions, and I will start with number one, because I have two very old pictures from a flame. Here you have a conventional technique extracting some amount of gas from this flame in order to make a gas analysis, in order to see what's going on. And if you look into this flame, it is disturbed by your probe. So when you use a thermocouple or whatever, you have an interaction with your flame and your measurement device. And when the flame is complicated, or when you have a gas flow which is complicated, turbulent or whatever, you don't know how to correct this very easy for a thermocouple, for example. When you use a laser-based measurement technique, as you can see over here, for example, the flame keeps its shape. You have, in principle, no interaction, no visible interaction with your flame. So it's a non-intrusive technique, which is very helpful because you measure really what's going on, and you don't measure a combination between your probe and your gas stream or combustion process or whatever. Based on this is very helpful. I mean, these techniques are more expensive and complicated. So the first idea should be, in order to get my measurement information, could I use a conventional thermocouple or a conventional probe technique? Is this enough? Or do I need more precise information? Or do I need more information? If you don't need, just use a thermocouple, fine. Keep in mind, it's not exactly the temperature, it's not exactly what you measure, so you need to make some corrections and so on. Okay. If you need it more precisely, concerning time resolution, concerning spatial resolution, concerning interaction, then laser-based techniques have a lot of advantages. Question number two was that we do not measure all the light which we generate with our lasers. We measure not the complete answer. That's right. But we don't, in the first step, we are not interested in absolute intensities. In the first step, we are interested in wavelength. That means the color of our signal is not changing, even if we have half of the intensity. And then we look at relative intensities. So when we look into different molecules, we get from each one half of the intensity. It doesn't matter. The relative concentration is still the same. When we measure all molecules in our gas volume, if we measure for all relative concentrations, then we still have the complete information from the measurement volume, even if we lose 10, 20, 90% of light. And when we measure temperature with these nonlinear processes, we also look for one molecule into the intensity levels of each energy level of this specific molecule. And we look in also relative to the next energy level. So it's not an absolute intensity measurement, but it's in a relative intensity measurement. Thereby, losing light is not nice concerning detection limits, but it's not a problem concerning our measurement information. I think that was good to mention.
Пожалуйста, еще вопрос.
У меня вопрос в продолжение вопроса профессора Шаркова. Вот вы разрабатываете методику измерений и проводите определенные эксперименты. Но дальше вот процесс внедрения, разработки каких-то приборов, пусть небольших серий, вот у вас как вот он организован?
Sie entwickeln Methoden und machen Messungen. Und was machen Sie weiter? Also zum Beispiel ein neues Gerät produzieren und verkaufen auf den Grund von Ihrer Entwicklung.
Thank you for this question. There are different options. One is, of course, building a device and selling it. The other option is to sell measurement techniques, to sell the possibility to be able to measure certain things. So, with our special devices, we can measure things for industry which they can't.
Was machen Sie?
We are selling this. And sometimes we build, sometimes we go to industry and do measurement there for them. And they pay for the measurements.
Еще, пожалуйста, вопросы.
Наших молодых коллег, может быть.
Молодые коллеги. Тут не слишком
Ну,
молодые.
немножко подробнее, может быть, о самой кафедре, институте, так сказать, кого готовят, какова магистра, так сказать, сколько вообще человек.
Так говорили же.
Нет, задать вопрос.
Он говорил об этом.
Говорил, наверное.
Im Institut. Welche Bachelor, was für ein Fachgebiet haben Sie dann? Welche Masterprogramme haben Sie und so weiter?
Yeah. Okay. When students are coming to our institute, they are coming when they study mechanical engineering. Most of them in a bachelor, in a master program. Because I'm a physicist, I studied physics. We could also offer thesis for physicists, for example, but most of the students are from mechanical engineering.
Entschuldigung, ich versuche korrigieren, weil bei uns Mechanical Engineering bedeutet, also die Leute verstehen ganz direkt. Bei Ihnen die Fachgebiete ist sehr breit im Vergleich mit unseren. Was bedeutet Mechanical Engineering? Иhren Sinn.
Okay, I show. Okay.
Я как раз и спросил, что означает. Здесь вот многие поймут, когда говорят инженер-механик, это что-то такое напильник или шестерню какую-то. У них просто вот эти сами специальности, они шире намного. Вот я попросил просто поуже объяснить, что это такое.
So all these institutes are within
Alles
mechanical
das Mechanical
engineering.
Engineering.
That's all mechanical engineering.
Все это вот инженер-механик.
So
На самом деле, посмотрите, тут и газодинамика наша, и теплообмен, там все есть.
within each institute there are 3, 4, 5 chair positions like me. And in total there are 22 professors with 22 groups working on 22 different subjects. And students can, for the bachelor or master thesis, they can choose a certain area out of these 22 areas. So they can choose here. I want to have some information about vehicle production technology, for example, how to build a car, how to build up a factory to build cars, something like this. If I want to do this, I can choose a bachelor thesis or master thesis here. If I'm interested in calculating a lot of things concerning mechanics, and I'm very fit in math and solving equations, I can go over here. If I'm interested in fluid mechanics, I can go within our institute, I can go to a colleague who's working on fluid mechanics and do my bachelor or master thesis there. So the system is that the students get a basic knowledge in a lot of different subjects, and at a certain point they have to choose certain subjects which are in this area, and then in the end they can start their bachelor and master thesis in this area. So, nevertheless, all have some basic courses, so everyone has to listen to thermodynamics, to fluid mechanics, and so on.
Пожалуйста.
Excuse me, what procedures students have to pass to enter at your university, for example, after bachelor, to study master course?
Okay. There is, first of all, it is interesting to know that how much semester is a bachelor. Here I think it's also 6 semesters, so that's first 8, even more. Better is more. More is better. Sorry. Then in mechanical engineering, we look if the subjects are more or less comparable. And then you could just start. In some other universities, they have some limits concerning your grades. Up to now, we are lucky we don't have, or you are lucky we don't have. Whatever.
Я чуть-чуть уточню, потому что одна из целей визита коллеги – это создание совместной программы. Потому что наши бакалавры могут на эту программу записаться. Wie gesagt, eine von Zwecken ihren Besuch hier ist eine gemeinsame Masterprogramm.
So right now it's also very easy to come to us to start a master thesis, for example, because we have a collaboration starting already, so that works already. If someone is interested, please come. We are happy about that. And I just want to show maybe one example concerning selling measurement techniques. Yeah, this is good. When we think about car companies, what they want is they want to reduce fuel consumption and emission. The engines, they build them more and more smaller, downsizing, smaller engines, less heat is going over the walls away, so the engines are getting more and more efficient. So the thing is, engines are getting smaller and smaller by having the same amount of power. And if you look into a diagram over here, that was some time ago, you can buy a 6-cylinder 2.8 liter engine with 155 horsepower, kilowatts, sorry. Nowadays, or what we investigated some time ago, 1.4 liter, 4-cylinder, twin-charged engine, again with 155 kilowatts horsepower. And the difference is a reduction of about 5% concerning CO2 emissions and fuel consumptions to this 2.0 liter, which was already a reduction of more than 7% to this 6-cylinder 2.8 liter. So this is what industry is doing with the engines now. Smaller engines turbocharger, 1 or 2 variable turbine blades inside turbochargers in order to make them even more effective. The question is, what happens with the engine? You put in your air under quite a high pressure, so you start compressing your gas already at a high pressure level. And when you have a spark ignition engine, you are limited with your compression ratio, because at a certain point, otherwise your mixture of gas and fuel will ignite by itself and not by the spark plug. And you want to ignite it by the spark plug when you want that it's burning, and not someone at some point. So these to control these engines is getting more and more complex, and to handle these engines, and that's quite difficult. And I've told that in Germany the amount of methanol in the fuel is increased from 5 to 10%, and sometimes to 50, maybe even more. There are regions in Northern Europe, I think Norway or something, where they have 85% methanol. And what happens when you change the fuel with these engines? We made tests in an engine test facility. Here you could see our optical access. It's just a few millimeters window. Our lasers go in there. Our signal coming on the other side out of this laser, so it's nearly a production type engine. It's very, very small modification. 155 kilowatts, running nearly full load. And our complex laser systems, 3 lasers, detectors and so on, were in this test facility. And we measured for different fuels the temperature during compression. And with an isentropic calculation, you can fit this curve to this measured temperatures. And when you see, this is for standard fuel, which you can buy in Germany right now. And this is for fuel which has a higher methanol concentration. Here, the temperature or the temperature during compression is lower. The reason is injection was over here, and you need more enthalpy to put methanol into vapor, into gas phase. So you need more energy, and this is coming from outside the air. So the air around is cooling down more when you use more ethanol. And you will not reach that high temperature right before ignition. So you have temperature difference here of several hundred or 60, 80 Kelvin with these 2 different fuels, and then the ignition starts. This is an important information for automobile industry, because they have to build engines which they could sell all over the world. In Brazil, where they use 100% methanol. In Germany, where they right now use 10%, maybe in future 15 or 20%. So when they sell an engine right now, you want to use it not just 1 or 2 years, you want to use it also 10 years, where the fuel is changing. So they need to know what happens when the fuel is changing. And these engine companies don't have these measurement equipment to see these things. And this is interesting for them, because then they know how to change the electronics of the engine to adapt to other fuels. And this is of course necessary. So this is just one example how we sell measurement techniques.
Что получается? Тут в тесный клубок сплелось все. Гидродинамика с газодинамикой, термодинамика, теплообмен, массообмен. Вот такой и плюс еще электроника управляющая. Учитесь. Электроника, гидродинамика, газдинамик, diese Turboladder ist auch.
Yeah, that's completely right. You need when you go, after you finish and you go to industry, you need a lot of background of a lot of different subjects. And that helps a lot, because you will talk with chemists concerning combustion process. In a gas turbine, in a in a coal power plant or whatever. You will talk with mathematicians who can calculate things. You will talk with physicists, you will talk with material scientist guys. And you have to understand all these guys, and you have to, or girls, and you have to organize them and to get results. And therefore it's very helpful when you know from each subject a little bit, that you can understand what is his problem, what is her problem, how can I bring these two together to get a useful result out of my group that I can solve problems. And that's what you can learn by looking into the different courses and learn these different basics. So that's important.
Вопрос еще по организации учебного процесса. Вы готовите бакалавров и магистров. Все ли бакалавры у вас обеспечены бюджетными местами? А если кроме бюджетных мест контрактное обучение? Сколько оно стоит?
Я знаю, как я ответил. Also, der Versuch vergleichen Ihres System und unser System hat uns mehrere Studenten studieren also Startbudget, und es gibt einen Teil, die müssen bezahlen, weil sie haben nicht genügend Noten, um für Budget studieren. Er fragt, wie ist das bei Ihnen?
In Germany, we had a certain small student fee some time ago. It was for Germany it was very small, but even that is not present anymore. So there is no fee for students. You can all come, but universities could choose their students. They have a certain limited amount of space for students, and when they can teach 100 students and if thousands are applying, they say, okay, then we choose, and we choose the 10% best. They are allowed to do that. So some universities right now, because all universities have a lot of students, they choose by the degrees of the students by their school degrees, if they take the student or not. For mechanical engineering in Siegen, there's also the possibility that we could choose students. We have the option. Still, we try to get everyone who's applying to get them also in and start. When you go to Munich, right now maybe 40%, 50% can start, and just by degree from school. My children, because I'm coming from Erlangen, my children grown up, they are living in Erlangen, they are studying there. Also in Erlangen, they choose from the degree the children finished school, and at some places like Munich, you had to have very good grades so you can start. But the point is, and the problem is, that you have to apply in each university you want to go, and each university has sending out the letter of acceptance at a different time, and they give you 1 week of decision. So you apply at 10 universities, the first one is sending you a letter. Should you choose it, or wait for the other 9? So it's a difficult thing. So what also my children did, they applied at Erlangen, and they applied at a university where they know, okay, there is no limitation. Because there I will get an entrance, definitely. And then they hope that these 2 letters were coming at the same time. And that is the situation right now. In Siegen, we are at the limit, but still we take all who apply. When you want to go to Karlsruhe or Munich, it will be different. But you never had to
Он
pay.
этот вопрос ответил, я еще раз уточню. А mein größere Teil von Studenten bezahlen für die Ausbildung gar nicht. 90% wahrscheinlich. Und ganz kleiner Teil muss bezahlen, weil sie haben Schulden und so und können nicht für Großbudget, Staatsbudget, Entschuldigung, Mittel studieren und müssen bezahlen. Gibt es was Ähnliches in Deutschland oder nicht?
In Germany, you don't have to pay for university, even if you're
Нет, хватит.
Конечно.
Что,
Я же говорил об этом.
Нет, меняется. Ну, а вот
Они социализм.
иностранные студенты, если там где китайские, как они платят?
Und die ausländischen Studenten, Chinesen oder bezahlen sie auch nicht.
no. Therefore, it's interesting for
Им даже стипендии. За то, что
Она же
дорогих. Конечно.
А вот
Ну, also der fragt, wenn unsere Studenten kommen, kriegen sie ein Stipendium oder nicht?
Sie können, they could come, they have not to pay for the university, but the question is living expense, housing, living, eating, and so on. That is the question, and that is depending. Some students can get an additional job for some hours in the different institutes to work as a student there to earn some money. Some also get some money from Europe. Some European countries, they get some money from Erasmus program. So there are some options, but in general from university they don't get any money for housing, for living, for eating, and so on. They just get the
Erasmus und so
yeah,
weiter.
they just get the education free.
Ну, самый реальный путь это вот то, что ты спрашиваешь. Это вот ДАД, допустим, или Erasmus, какие-то программы получать на стипендию.
нет, ну, при таком коммунизме все равно должен быть какой-то барьер, какой-то конкурс, еще что-то. Не может быть, что любой захотел и учить. Не может быть.
Это факт. Es gibt bestimmt ein Barriere für ausländische Studenten. Gibt es zum Beispiel Anzahl mehr als kann man nicht? Oder
The point is, we up to now this was not necessary because the students, not all will get some money out of these programs. They have to apply for these programs. When they get money from these programs, they have to be very good. So when they don't get money for this program, they need to have money for living somewhere.
Mm-hmm.
And living in Germany is not that cheap. So you need to get something like 1,000 euros per month for living somewhere.
What? So as a student, I think you need like 400 or 500 euros. So that's for me at least. I don't think more. Or maybe there are some.
It's depending on city.
Yeah, of course, in München there would be some problems.
It's depending on city.
Yeah, that might be true.
My daughter has an extremely cheap flat in Erlangen. She already is paying nearly 400. And that's extremely cheap for Erlangen.
Okay. Well, I've studied in Jena, and
That's cheap.
well, Jena is one of the more expensive cities in the east, but it's
still cheap
Still
compared
cheap
to
here.
others.
Yeah.
Так, ну что, еще вопросы есть? Может быть, закончим на этом, а то мы уже гости утомили. Тяжело все-таки вот так. По режиму громкоговорителя, долгое время говорить, отвечать.
Ну, все, потому что
У нас еще дальше очень много всего. Да.
сегодняшний день.
Ну что, тогда поблагодарим нашего гостя.